Welcome to antenna as a component. In this video, we'll discuss about antenna losses, efficiency, and the generalized Friis formula. So the purpose of this presentation is to understand losses in real world that affect the received power. Then we will define antenna efficiency and its various components, and finally we'll extend this to more generalized form of the Friis formula by including these loss factors. Here we will discuss various types of antenna losses which cause degradation in the antenna performance. First is the conduction and dielectric loss. Conduction loss means undesired ohmic resistance which appear due to conduction losses. Dielectric losses is due to substrate loss, and this happens because antenna sometimes is implemented on a dielectric substrate, some higher order modes, some radiation into the substrate which is not in the free space is considered as loss. The second type is mismatch loss. If there is imperfect matching between the source and antenna impedances, this will cause what's called reflection coefficient, which is also translated as a loss. We have also what's called the polarization loss. This happens due to polarization mismatch between the transmitting and receiving antenna. We'll discuss in detail. Finally, there is other type of losses, more specifically atmospheric attenuation, and this actually happens due to either something like water vapor or resonance with some molecule, like at 60 gigahertz here we have some resonance with oxygen, for example, O2 resonance, and this is translated to loss. Now we will translate different type of losses into efficiency. We start with radiation efficiency, which take consideration of conduction and dielectric loss. And how it is calculated: if we assume we have a total power supplied to the antenna, and a part of this power which is radiated, but another part which is losses. If we form this one as in terms of a circuit, it will appear like what we can see here. And if we assume a total current I naught following through this network or circuit, so the power loss will be in this R loss, and the desired power is the power in the R radiation. So we can write this as these two equations: B radiated is equal I naught squared R radiation, and B loss is I naught squared R loss. And we can then simplify to this well-known equation: eta radiation is just equal to R radiation divided by the summation of R radiation and R loss. Where this come from? Just we substituted because we have R radiation will be B radiation over B total, and just substitute with these two equations, you will get the final equation here. The second form of efficiency is the mismatch efficiency, which take into consideration the mismatch loss due to the difference between the system impedance Z naught and the input impedance Z input. Because if we have a matching circuit that match our antenna to the source, this matching circuit at its input, we will see some kind of impedance, and if there is any mismatch between Z input and Z node, this will cause losses. First, this will be translated into what's called reflection coefficient, which is calculated using this equation here. And then if we want to calculate the mismatch efficiency, since this one is just impedance, then we in order to see in terms of power, we need to make a square. So magnitude of gamma square is just the losses. If we make subtraction from 1, we will get our efficiency. Now we are with the third type of mismatch, which is polarization, and we define for it what's called polarization loss factor and efficiency, which quantifies the reduction in the received power due to what? Polarization mismatch between what? Between our transmitting antenna and receiving antenna. When we define eta polarization, we will find another term called PLF. It is the same concept, which is equal to cosine square alpha, and alpha is just what is the polarization mismatch angle between the electric field vector of the transmitted wave and the receiving antenna polarization axis. So if the electric field of the transmitted wave is rho1, I mean its direction, and the transmitted antenna, say rho tx and rho rx for the receiving antenna, then if we make the dot product of these two vectors, we will have cosine alpha. And if alpha is equal to 0, then our polarization BLF will be 1. If alpha is 45 degrees, you will have 1 over the root of 2. And if alpha is 90, we will have 0. I mean the cosine alpha. This means that this one is very critical, and we need to match the polarization of the transmitting and receiving antenna as possible. Now we reach the total efficiency, which combine all the efficiencies which we have discussed: the radiation efficiency, the mismatch efficiency, and the polarization efficiency. And there is one fundamental note here we need to consider, that eta radiation, there is two antennas, right? This is a system. It is not a one-sided system. It is two-sided system, transmitting and receiving antenna, and each will have its own radiation efficiency and also its own mismatch efficiency. For polarization, actually, it happens between both of them, so it is not repeated. Before, we have studied what's called the basic Friis formula shown here. This time we will study about the generalized Friis transfer formula in order to include the loss effects represented by the eta total, the total efficiency. And now this one represents the actual received bar in the receiver after determination of all losses. And there is something called a dB4. Simply, if you take 10 log of both sides here, you will because multiplication will turn into summation. Of course, here minus, because it depends on how we write the losses. And then we have some definitions. L is just losses introduced by the efficiency. We can say 10 log 1 over eta total. And the free space path loss, FSPL, is determined as 20 log 4 by r over lambda. And here was 2 in before. This was actually 10. And if we use the log characteristic, it will 10 by 2, which is 20. Just to note, we know that the gain is NdB, loss is also in NdB, but very important note that power here is this is not a ratio, so we give something called dB watt as a representation. Finally, we are with the takeouts of this video. We have learned that antennas are not 100% efficient. And we have also learned that we have several factors that affect the efficiency of the antenna, like conduction, mismatch, and polarization. And at the end, this will be translated as a reduction in the received power at the receiver side. And we have learned that we can revise the transfer formula of Friis to a generalized one by introduction of eta total. Stay tuned for more videos.